loop antenna. So we are going to discuss about wired loop antenna here. So when we talk about the loop antenna, it can have any shape, but it should form a closed structure. Now the loop antennas, they are categorized as small loop antenna and the large loop antenna. When we say small loop antenna, then how small actually? So it's not like if any loop antenna which is appearing very small, means it can be fitted in pocket, or it can be fitted on your palm. So it doesn't mean that it is small in size. And when we say it is large, so this criteria is actually not applicable. But when we talk about small loop antenna or the large loop antenna, then it totally depends on what is the size of the loop with respect to a wavelength. And when we say wavelength, so it is that wavelength at which this antenna is operated. So every antenna is designed for certain frequency. So frequency and wavelength, they are connected. So if the size of circumference of the loop is less than lambda by 10, then we say that there is a small loop antenna, and if it is larger than that, we say it is large loop antenna. There are other ways also to define it, but it requires some mathematical background of the loop antenna, so that we will discuss later on. But roughly, this is how we have to differentiate between the small loop antenna and the large loop antenna. So if the size of the antenna is very small, then there are certain characteristics of that antenna, and that can be defined with the help of what? Current, which is flowing through one antenna when it is excited with the help of a source. So if the current at each and every point along the wire of the loop antenna, if it is constant, like here we are saying that it is I phi is the current through the thin loop, and that is equals to I naught, which is a constant quantity. So what happens that in a small loop, the current at every point is going to remain uniform, same. This is one antenna, loop antenna, you can see, and this is the I phi which is flowing through this loop, and the current I phi is constant. It is equals to what? I naught. And we are going to check the influence of this current flowing in this loop at a distance r. R is the distance measured from the center of the loop to any observation point, whereas capital R is the distance from the small segment of the loop to the same observation point. Okay, but in general we refer this small r, because that is the correct distance, because every antenna, whatever be the size of the antenna, but it will have its one reference location. So that reference location is nothing but the center of the loop antenna. Now the fields, if current is flowing through a loop, so you can see that the current is flowing through a circular path. So it is considered that the motion of the electron will be what? Accelerated in nature. And any accelerated charged particle is capable to radiate out magnetic field. And if a magnetic field is there, it can generate electric field if the magnetic field is function of time. So here we are exciting our antenna with the help of a sinusoidal current. Now that current is going to give you vector magnetic potential. Vector magnetic potential is a hypothetical concept, but it is very useful to derive electric field and magnetic field once current is known, which is flowing through any antenna. So here also you can see that vector magnetic potential A, which is function of current I naught. So magnetic potential, it is always along the direction in which the current flows. So the vector magnetic potential can be utilized to find out vector magnetic field. So here we have got two components of magnetic field, one in radial direction and another in angular direction. And magnetic field in the direction of phi is 0, because magnetic field and this current, they are always orthogonal to each other. So if the current is already flowing in the direction of phi, so magnetic field cannot be in the same direction, it must be perpendicular to that. So theta is the only component which is one of the components which is perpendicular to the phi. And both the fields, they are part of the far field zone, because we are more interested in what is happening in the far field region than in what is happening in the near field region. Now, once the magnetic field is known to you, you can find out electric field. So here you can see that electric field in the direction of theta and in the direction of r is going to be 0, because already the magnetic fields are there. So electric field and magnetic fields, they are always perpendicular to each other. So you should get, if you are having magnetic field in the direction of r, then electric field in the direction of r should not be there. So the electric field is there in the direction of phi. Why? Because when a current is flowing, so there has to be some force which is responsible for the motion of the current, and the current is what is flowing in the direction of phi, and the force which is responsible for the flow of current is what? The electromotive force. Okay, that's why the electric field will be in the direction of phi. Here A is the radius of the loop, I0 is the maximum current, actually it's a constant current. Small r is the distance between the antenna location and the point of observation. K is propagation constant. Okay. Theta is the angle made with respect to the z-axis. Now we are knowing the electric field and magnetic field, so we can find out power density, and from power density we can find out power, and finally we can find out radiation resistance. So to find out power density, we can use Poynting theorem. So here we are using Poynting vector, which is 1/2 E cross H conjugate. So E and H both are known to us. E, there is a single quantity which is in the direction of phi, whereas H, it comprises of two different quantities, one in radial direction, another in the theta direction. So cross product of these two will be 1/2, then in bracket minus AR E phi H theta conjugate, and A theta E phi HR conjugate. So if you substitute all these, then you get a power density, which is written here. From power density, we can use the divergence theorem to find out power. So it is W dot ds, an integration over the entire surface, over the entire spherical surface, you can say. So finally the power is eta times of pi/12, and Ka raised to 4 I0 square. Now from this we can find out radiation resistance, because power is always given by what? I square into R. So if I equate this power equals to what? I square into R. R is unknown quantity, we have to find out. I square is the current which is flowing through antenna. So I square is nothing but your I0 square only, that will get cancelled out. And finally you get a radiation resistance here. So you can see that the radiation resistance is given by eta times of pi/6, and then K square A square the whole square. Area, it can be, the A is what? Radius of the loop, so it can be expressed in terms of what? The area of the loop and the circumference of the loop. That's why you are having two more expressions of radiation resistance. Here is one example. Find the radiation resistance of a single turn and 8-turn small circular loop. The radius of the loop is λ/25, and the medium is free space. So there are two loop antennas whose size is what? Same for both the cases. Both are having radius of λ/25, but both are different. One is having a single turn, another is having 8 turns. So the surface area of this loop is going to be pi a square. So radius is given is lambda by 25. So we can find out the area. Now we want to find out radiation resistance for single turn. So we can refer the earlier formula there. So we have calculated what? Surface area. So we can use the second equation. Sorry, the last equation can also be used because the area is in terms of lambda. So 31,171 S square divided by lambda raised to 4, that can be used. So for a single turn it is coming as 0.788 ohms. But if it is 8 turns, then the same quantity will get multiplied by 8 square. So it becomes 50.43 ohms. So you can see the difference in the radiation resistance. Now the radiation pattern of small loop. So on the right hand side we are having 3-dimensional radiation pattern, and the left hand side we are having 2-dimensional radiation pattern of the same antenna. Now here the little portion of the 3-dimensional radiation pattern is taken out so that you can visualize the 2-dimensional radiation pattern. So it is nothing but a donut shape. But here on the left hand side we are having multiple donuts. That is happening because of the different size of the loop antenna. So the thick curve is for a radius of 0.1 lambda is lambda by 10, small loop. And as the size increases, it is observed that there is little change in the shape of the radiation pattern. The initial applications of the loop antenna was restricted to pagers and the radio. Like in radio, if you open the old radio, then you can find out there is a iron bar is there. So ferrite rod is there, and that ferrite rod there are copper turns are available. So those copper turns are nothing but the loop antennas only.